Hi, thank you for tuning in. I'm Jennifer Kakshori. You're listening to the ETH Podcast. In our last episode, we reached for the stars with the only Swiss astronaut, Claude Nicollier, and also with an aspiring astronaut, Judith Soulagi. And in this episode, we continue to hear about the universe and talk to two ETH scientists with different perspectives. One of them is Domenico Giardini, and the other one is Adrian Glauser. First of all, Domenico, where are you right now?
Oh, I'm in a wide definition of home office. I'm in Cagliari, which is a bit far away from Zurich. But on Zoom, we are all in the same office, so my room is always open.
Adrian, where are you?
I'm at the ETH Schönkeberg right now in my office.
So I would like both of you to introduce yourself. Domenico, maybe you go first.
Yes, I'm a professor of Seismology and Geodynamics since 25 years at ETH in Zurich. I directed the seismological service of Switzerland for 15 years. And after that, I changed and I moved to coordinate the national research on energy supply for the energy transition. In terms of research, I participate in two space missions. One is LISA for the detection of gravitational waves from space. And then I have a seismometer running on Mars on a NASA mission.
We'll speak about the seismometer later. Adrian, please tell us what you do.
Yeah, I'm a senior researcher here in the group for exoplanets and habitability in the Institute for Particle Physics and Astrophysics. I'm leading the laboratory for astronomical instrumentation. That's also because I am an astronomical instrumentalist, as I call myself, meaning I'm developing instruments for the largest telescopes, both on ground and in space.
When I look up into the sky and see the stars and the moon, I always think about my childhood and how many other people in history have seen these stars and moons hundreds and thousands of years ago. And somehow I feel connected and very calm, but also very little. Is this something you know as a feeling as well?
Yeah, in a sense, the Earth is always very noisy, very full of people, very full of everything. And when you look up, of course, you lose a bit the dimension. Things are very far away. They are bigger and noisier than the Earth. The Earth, in comparison, is a small place where almost nothing happens other than our own lives in terms of big scale. But obviously, we're looking from far away and trying to understand that things that appear only as small specks far away is very difficult and very challenging, and it moves a lot of your own energy to it.
And you, Adrian, do you have this sense of remembering childhood as well and feeling moved when you look up into the sky nowadays?
Absolutely. I mean, for me, this was always the most inspiring part, looking up and thinking about the infinity. And also reflecting about our own space here and our place in the universe. How unique are we? Are we unique, or is this something that just must happen? This is now, on a professional level, a question I still try to answer, at least a small piece of it.
Do you both remember a moment, for instance, in your childhood that led you to what you do today?
Yeah, absolutely. I mean, I think I was 10 when I knew that I want to become an astronomer. The first telescope was a gift from my grandpa. Since then, I never really left this fascination. And although I studied physics and not astronomy, it was always clear that I want to end up as an astrophysicist, and finally became one.
And you, Domenico, was there a magic moment in your life?
In my case, it came later. Of course, it's impossible not to be fascinated by astronomy in general. So I had a small telescope at home. I was looking at things, trying to keep following stars and so on. So all of that we have done as kids. But professionally, I started looking inside the Earth. And in 1996, there was a French mission that wanted to bring a seismometer to Mars. And it just blew up on launch. And then I got attracted to it. We started talking to the French colleagues, and I said, sure, what we know how to do on Earth, of course, on Earth we have 5,000 seismic stations running, but if you go back 100 years, on Earth we had only single stations, and nonetheless, the people 100 years ago understood the interior structure of the Earth. And if you do not understand the interior structure of a planet, you don't understand the planet. And so that's what moved me, in a sense, was a bad episode, the loss of a rocket with seismometers on board that actually brought me to say, okay, but we can do it better. And then it took 25 years, but now we are on Mars.
Adrian, together with many other people, you worked on the James-Webb-Telescope, the largest telescope ever, and it's supposed to uncover the origin of the first galaxies. The James-Webb-Telescope is to launch this fall. What does this mean to you that it will leave planet Earth in the fall?
Well, first of all, it's a big relief if it finally does, because I'm waiting for this moment for many, many years. I started 18 years ago, actually, being involved in that mission. It got delayed for various reasons, several years, and I'm seeing that now coming to an end. And then still we will be involved for the first 6 months for commissioning support. Yeah, it's a big relief and reward as well. And having been able to contribute to the world's biggest space telescope, just to precise that, is also, I'm looking very much forward to all the discoveries that will be made with this facility.
You just mentioned that the launch was delayed a few times. It was originally meant to leave 10 years ago, but it's common that schedules of projects of this size get postponed and change a lot. Do you need to be patient as a researcher in this field in general?
Patient and stubborn, I would say both. And many colleagues that were part of the project left, either because they got retired or they looked for other positions. I was lucky enough to still be involved in that mission, so I think it's also a privilege for me. Yes, you need to be patient, but it's not that this would be the only project I'm working on. I started because I was impatient also to now being involved in the world's biggest telescope on ground, which is the extremely large telescope. And so that makes me busy right now, and more actually than the James-Webb mission.
And Domenico, you're lucky. Your instrument is already on Mars. Did you need to be patient with that as well?
Yes, you need to consider that the last seismometer on Mars was in 1976, and they didn't record anything because it was located on the lander on the Viking. These were the American Vikings, and so didn't have any recording. And so it took decades to convince either ESA or NASA to actually go up there with the seismometer again. And ESA so far, so the European Space Agency, never landed successfully on Mars. You need to consider that Mars looks like nearby and easy to reach, but more than half of the missions that were launched to Mars, and there are now 45 of them, either missed Mars or they arrived to Mars way too fast and crashed, or they simply got lost way before going anywhere. And for every successful mission that gets launched, there are at least 5 of them that get to a certain level of developments, and then there is no funding or the priorities are changing. So it's a business that it's a lifetime business. And usually we think that reaching a planet is easy. It's there, you reach it. It is not at all. Actually, what you do is that, contrary to the James-Webb doesn't want to meet anything in sky, but we have an appointment with the planet. So after 6 months, we are on the trajectory, which is the orbit, followed by Mars. And then Mars arrives very, very fast. And then you have to make sure that everything is very, very precisely timed. Everything works well so that the planet doesn't crash you, because it's a big planet going very fast.
What is it about Mars quakes that interests you? Why are they so interesting?
There are 2 reasons. First of all, we have them, which is good. If we had landed there and we had no Mars quakes, we would have been very disappointed. But we do have them. And it's amazing what you can do with a single station and a few quakes on a faraway planet. I mean, you can see where the core is, how large is the core. Until now, from rotation parameters, we knew there was a core, but we couldn't go much further than that. The uncertainty was huge. Now we nail it. We know the mantle conditions. We know the depth of the crust, the lithosphere. I'm using technical terms, but what it means is that we now can see inside the planet and see how the planet is built. And we can start discriminating why did it go in a different direction than the Earth or not. For example, that planet had oceans and an atmosphere in the first billion years of its life, and then everything went away. The most likely cause is because it lost a magnetic field. The magnetic field depends on how the core rotates and works. Why did the core slow down so that there was no magnetic field, and could it happen on the Earth? Usually you see these things in movies, but actually here you see it on other planets. They're there, and you can really look at it now that we look inside. The second aspect, of course, is that the planet, if it has quakes, it means the crust is active. It doesn't have plate tectonics, but it's subject to strain, to stress, exactly like the Earth. So we can see the geology, we can see the faults from above, from remote sensing, actually better than we see on the Earth. But we now see what happens inside the crust, and so it tells us where it is deforming and how.
And does it teach us anything about planet Earth?
Yes, it does. Of course, today we know about 4,000 exoplanets, as they're called, so planets which have characteristics similar to the Earth, but in other stellar systems in our galaxy. But those planets are very far away. We will at most know a few parameters from them. But Mars is a planet on which we can actually walk, in a sense, quite soon. We will, if possible. But it's a planet from which we can learn why did it follow a path so different from the Earth. I often show two slides to my students. One is a slide from above, of course, an image of the geology of Mars from above, and one is from Arizona. You cannot distinguish the two. We are not so far away. All of our world could be desert like in Arizona or Sahara. We are not that far away. So understanding why a planet, what parameters change on the planet in order that the planet takes a different path than another, and why we have life here rather than on Mars. Did we have life on Mars, and how did it end? So these questions are crucial questions for us.
Adrian, what crosses your mind when you hear Domenico talking about having his hands on Mars already?
Well, I'm jealous for two reasons. One is he went over the risky phase of the mission and successfully passed it. The other is that indeed he has the possibility to examine a planet that is close, and he can examine it with a parameter space that is inaccessible for us. In that sense, I'm quite jealous because all the exoplanets we are going to observe, we have always indirect indicators, and if we are very lucky in the far future, we might also see indications for life, but we will not have the same measurements being able to conduct in all those exoplanets. The difference, though, is that we have, because we observe exoplanets, we have a very big variety of objects, and that also constrains questions of how life on Earth actually can happen. And so it's certainly complementary, the two fields.
And both of you, in a sense of time in the context of space, is on a much larger scale than our lives. What is it like working for things you might not witness anymore? Adrian, you're working on a future telescope, as you told us, that will be in use at the earliest once you retire. What's that like?
So you refer to our vision that we would like to launch a space interferometer that really allows us to probe Earth-like planets around other stars. And for that, you need to go to space. You need to go with very long so-called baselines in order to get the spatial resolutions we need. And yes, this is a very ambitious project, and hopefully I will still be alive once such a mission is flying, but maybe my professional life will already be over by then. And yet I'm extremely motivated to do it, because I think contributing, even if it's a very small piece, to the big puzzle is already a big reward for me. And I think the question at hand, how unique is life on Earth, is so fundamental that I think whatever I can do to contribute to a small part of it is already sufficient. Even if the answer might be we don't find life outside of Earth, that would be also good enough for me. But at the moment, we simply don't know. So that's not good enough yet.
And Domenico, what's it for you? I mean, you were lucky enough that what you do actually already happened throughout your professional life, that you can measure the Mars quakes. But what's it like working with these time dimensions that are much larger than a human lifetime?
When you talk about this large-scale infrastructure, it is normal. I mentioned before, you can try for 30 years and then you don't fly. Or you fly and to watch a rocket with 30 years of your work blowing up after 100 meters is the worst thing that can happen to you, in a sense. To me, it did not happen so far. But I'm working on what's called the LISA mission, the Laser Interferometry Space Antenna for the Gravitational Waves. And if we are lucky, that will fly in 2037. And we started working on it 20 years ago. And so the preparation time of such a large mission It's really decades. It's over 2 generations. And I will not be professionally working anymore. I hope to watch it from the beach going up. I hope to see the results. But we are training the young generation of scientists that will use those data, that will be senior scientists by the time that mission flies. But you have to do it. If you don't do it, we go nowhere, in a sense. If we only look at what we can achieve within 2 years, the bigger things require commitments also of our own funding agencies, space agencies, and so on. So you plan to fly, for example, electronics that will exist 20 years from now, not electronics of 20 years in the past, because that's already long gone. And so planning the future in this way, you develop all the next generation of electronics that also will be used on the Earth and so on. So you really go far ahead of where you are now, because you have to anticipate conditions of a good 15 to 20 years from now. And it's always very exciting. So I don't mind if I won't be there on the day that the equipment starts working. I think we should all contribute to these bigger infrastructures.
So you're both working, in a sense, in space science. Where do you see the chances and the challenges in this field in the perspective of a nation as small as Switzerland?
I think the dimensions that we just outlined for the big missions that we were referring to is just clearly indicating that for future progress, a single country, whether it's a small or large, cannot really completely do it on its own. I think only international collaborations, and this goes even beyond the European border, I would say. I think it's really a global effort that one needs to do in order to make the next steps. And I think in research one is used to global collaborations, but also for this kind of projects where unfortunately still national interests are sometimes very strong, one has to overcome this perception and start working also on a national space agency level in a very collaborative way. The James-Webb is a good example where this happened. It's a collaboration between the US, Canada, and European countries. But I think for the space interferometer we are talking about, the European scale might be too small, and we clearly need to get everyone involved that can.
In space, things have become so large and so big, the so-called large class missions, that to compete, it doesn't make any sense. So in the moment, there is still competition with China and or Japan, but mostly China, not always aligned, so they do things on their own, which is okay. It's healthy competition in a sense, but there is very little point in launching the same instrument twice. And in the past, this happened too often between NASA and ESA. The instrument, one slightly different, one slightly better than the other, but in the end, the difference was not so much. So on the large class mission, this type of global approach is absolutely required. Otherwise, you just lose interest and money and everything. And they are all like this now, all the large class missions. And the smaller missions, of course, they're different. Switzerland was a major player on a mission to observe exoplanets, Cheops, together with ESA, of course, but a major player that is a Swiss-dominated mission. I think, however, that Switzerland can really put its hands in sensors and specific parts, systems that are flying, because with those, so in a sense, we should leave to the big countries that have strong space agencies and strong national industry that can actually act as what we call prime. So that means putting together entire missions. Switzerland usually doesn't do that. Switzerland is extremely strong in assembling individual instruments because we do them better than the others do. In many cases, our industry is very, very specialized in electronics, mechanics, optics, and we can do wonderful things in Switzerland. And this is why we're always preferred partners in many space missions.
Do you see any chances for Zurich or for ETH Zurich to have its position in this international field?
I mean, the efforts we undertake, and also in the context of the announcement for the funding of the Center for Origin of Life, I think we also here at ETH build up here a critical mass that allows us also to lead scientifically projects on large scales. That doesn't mean that we will fund everything ourselves, but clearly on a scientific level, I think we do have the aspiration to have a leadership role here.
Both of you comprehend on a scientific level how small planet Earth actually is in the big picture. What does this knowledge of this size, of the dimensions, what does it do to you as people, as Domenico and as Adrian?
It makes us even smaller. We are in a small speck on a small planet, on a small galaxy, everything is on scale, of course. It really begs the question of what else is out there. I mean, the reason why I started working, for example, on LISA, this is the gravitational waves. Gravitational waves, we picked a few of them using Earth ground instruments, LIGO and so on. This was 5 years ago. But really from space we will see. And what normally we don't realize is that we see, in a sense of seeing with our eyes or with our electromagnetic bands, infrared, ultraviolet, X-ray, gamma, we see only 5% of the universe. We know that 95% of that is not visible through electromagnetic waves. And that's why we're trying to look with that. So it's like you go underwater in the night without any mask, and then you try to understand what you're seeing. I mean, we really see only 5% of it, and in a sense of seeing, so we can measure things only from 5% of the energy and mass that sits out there. And the rest of the 95%, we haven't even started. And so we are looking forward in the future to major discoveries, and that makes us every time smaller and smaller.
Adrian, what does it do to you, the whole question of dimension?
I think it makes the view on Earth even more valuable. And I think knowing that we are able to live on this precious place that might be, if not unique, it's certainly isolated for quite some distance and probably unreachable distance, that makes it just more clear that our view, although I'm someone looking outside, should be more on the view on the planet itself, and that we keep care on its future.
Thank you, Domenico Giardini. Thank you, Adrian Glauser. Adrian mentioned the new center at the ETH Zurich looking at the origins of life. And one person who will move to Zurich to help establish this new center is the Swiss Nobel laureate Didier Queloz. And we will talk to him in the next episode of the ETH Podcast. My name is Jennifer Kakshuri. I produce this podcast together with Tiswachter's Audio Story Lab and sound designer Luki Fretz.